Today's topic, as you can see on the screen, is robots and humans working in harmony in the DC. Our presenters today are Krishna Venkatasamy, Chief Technology Officer with Lucas Systems, and Dave Cole, Principal Application Consultant, also at Lucas Systems. So with that, let me turn it over to Krishna.
Thank you, John. Good afternoon, everyone. As John introduced the topic, it's about the harmony between the workers and the robots within a warehouse or a distribution center. So at Lucas Systems, over the last 20 years, we've been in the business of optimizing work within the warehouse and applying mobile technologies to that optimized work, and whether it is to make the pickers and the operators within the warehouse more efficient, or to drive systems like conveyor systems or other automation within the warehouse. So that's what we've done traditionally within the warehouse. As robots have become more common or becoming more prevalent in the market, what we've done is at Lucas, we've looked at how we can take our knowledge, intelligence, and the software that we've built over these years and apply the same techniques or similar techniques to ensure that the work between the operators and the robots, that is the collaborative work between the operators and robots within the warehouse, is done in an efficient manner so you can achieve the objectives, whether it's productivity improvement or cost savings that you're looking to achieve. You can achieve those, and you can achieve those in an optimized fashion. And that's the topic for discussion today. Before we get into the actual use cases for how we plan to implement or have the software to implement these use cases, I'm first going to take a minute and walk through the different scenarios in which robots are starting to emerge as use cases or scenarios within the distribution center. We see four major emergence of use cases or scenarios. The first one is robots that are purpose-built to do cycle counting function within the warehouse. So they're basically autonomous, and they work through the warehouse counting the locations, either using RFID technology or through scanning. This is interesting, but again, this is not what we're going to focus on today. We'll get to that in the end. The second use case is a use case that was popularized by Kiva, which is now acquired by Amazon, where goods are brought to the picker or the person who's going to pick and fulfill orders. As you can see from this picture, that's a Kiva robot at the bottom. They're basically moving these racks of products that are randomly slotted store them and bring them to the person who's fulfilling the orders, in this picture behind them on the floor rack. Again, an interesting use case, but this is not what we're going to focus on today either. The third use case is where robots go to the goods and collaboratively work with the pickers. And this is one of the use cases we're going to spend most of our time talking about, where there needs to be cohesion and collaboration between the person who's picking the product from the pick location and fulfilling those orders that are on that robot. They're going to have to pick the product from the location and put it into one or many totes that can be on these robots. The picture you're seeing here it has only one tote. However, there are robots that can carry multiple totes on them at different levels. To us, to the software that we have, that is immaterial. That is, we can work with one tote or multiple totes. The focus for our software is to harmonize or make the collaboration between the person and the robot and the orders that the robot is trying to fill more efficient. And that's what we're going to spend most of the time talking today. The last use case is using robots as mobile conveyors. I'll let Dave Cole dig a little deeper into this technology and walk us through the use case. Dave?
Thanks, Krishna. So I'm going to walk you through a couple scenarios today The first one in fairly detailed, and the second one we're just going to touch on. So the first scenario is where this robot's coming to where the goods are going to be picked, and it is the robots going into the aisles to the pick locations. So as we walk through the first scenario, I'm going to first walk it through how most robots are handling it today, with what we call robot assisting the human. So to set up the scenario, you see the blue rectangles there. We're going to consider this a plan view of a shelving in a warehouse, and see the pick locations are the little ovals on the shelving. We've got 3 robots being fed by up to 2 pickers in this scenario. Right now, you see 1 human in there, human 1. We have 3 robots. 2 are stationary by their pick locations, and robot C up in the right-hand corner is entering the zone. Often systems today, the robot systems today, will have these pickers assigned to zones where the robots will then travel to the zone, and the picker will stay in his zone. The zone might be a set of aisles that they're restricted to or staying in to pick. The robots, as Krishna mentioned before, can be carrying 1 or more orders batched to it. So we're going to go ahead and start the presentation. So you see the human walking. He saw robot A, and he walked up to A, and he makes the pick on A. As he does that, you'll see A move away. He's looking for the next robot to go to, and he saw robot B down the aisle, so he walks down the aisle to robot B. And as you see there, once he made the pick from B, now C has entered that aisle, and he walks back up to make a pick at C. This process continues. He makes the pick at the next one to C. And now you'll also notice in the scenario, a second human picker has joined and has come into the zone. That's picker 2. 2 is looking for a robot because there's no direction to him. He knows he's come into the zone. He's looking for something to work on. 1 continues to pick. 2 finds a robot. 1 walked on to the available robot B. And they continue out picking. And if you notice here, 1 went over further in the zone and is continuing to pick in that zone. There's nothing telling them that there's not enough picks left for the 2 of them to work on. All right, so the next scenario is the same scenario, but we are now going to add coordination of the human and the robot. So the coordination will help improve what they are doing. Before I start, one of the advantages of the dynamic work optimization that Lucas provides is to improve capabilities of real-time batching. So it significantly reduces travel. We're not demonstrating that in this scenario. We are using the exact same batched orders as the previous scenario, so we're not taking advantage of that. There would be an additional improvement based on what orders you put together if you're doing more than 1 order on a robot. So as you noticed here, the human 1 did the exact same started out by moving to robot A, and as soon as he made the pick, he's instructed through a headset to go to the pick location directly behind him, because the system knows that robot C is in close proximity and will be there before he could walk to any other pick. So it's going to save him that walk distance that he walked previously by just directing him to turn around and pick from the location behind him. He now proceeds down or is directed to the next pick location also for Robot C. He's now directed over to an aisle next to him to Robot A. Even though there was a robot in the aisle that he was standing in, he did not proceed down to B. He went over and picked to A. Once he picked A, he then moved to C, and you'll notice our second person has now entered the zone. Picker 2 was directed to a location. He's heading there. If you notice, at this point, Robot B repositioned. The system is able to reposition not only the humans or direct the humans, but also be able to determine it's better if that robot comes over here because this human can get to it and follow the path coming backwards. Picker 1 is completing their picks and finishing out. You see 2 also doing the same. The system now determines that there's not enough work for both of them after he picks this last pick in B and sends human 1 off to another zone or area of the warehouse to finish or complete their other work. So this is showing the path that the first scenario where it was not coordinated between the picker and the robots, and picker 1 traveled approximately 412 feet to make that as 9 picks. If you take the next look at the second path, with the coordinated effort between the robot and the human, that travel distance went down to 202 feet. So it's approximately half the distance walked by the human. By doing this, you're making both the human and the robots more efficient. So you will be saving on the number of robots you need by making them more efficient, as well as obviously saving a lot of walking time and time spent by the humans moving around the warehouse. All right, so I'm going to touch now on a different scenario. And as I noted earlier, this scenario, we're not going to dive into this level of detail we just showed on the previous one, but just wanted to talk about how this works, and maybe in a future webinar we will dive a little bit more detail into this. This scenario, if you see the picture on your screen, is using a cart that is transferred by the robots, and the cart itself is wheeled down the aisles by a human as they pick. So we'll walk through. First of all, we're just so we've all seen warehouses that look similar to this. Obviously, this is just a presentation of a section of a warehouse with conveyors that are feeding in and out of zones. And this typically, anybody that's been in these realizes that conveyor systems, as valuable as they are, they cause barriers to movement of product and people through the warehouse. So people have to walk through gates or walk around conveyors to get from zone to zone. It blocks off powered equipment to get product in for replenishments and so forth. So that they do provide some barrier, but they also obviously provide some value. So we want to think about this in being replaced by or supplemented by robots. So the first advantage you'll notice, by removing that conveyor that was down at the floor level, you're able to add more shelving and more storage space. So that's the green sections of shelving that are showing here have been added to the floor plan. So I get more pick faces in my warehouse. And there isn't a warehouse or distribution guy that doesn't want more space. So it's by eliminating that conveyor that causes me to break my aisles up. I get that added feature. I also, by eliminating that conveyor, you provide the ability to go from zone to zone without having to walk around the conveyor or through a gate. So my sequence of which I'm picking can come directly from zone to zone. So as an example, I could be picking a cart in zone 5 and have picks in zone 6. Instead of having to pick through 5 first, then over to 6, I can walk straight across from 5 to 6. So I can, again, improve travel by not putting these barriers or conveyors in. So the key down in the right-hand corner is the text is a little small, but if you can see it, the key is there's green box squares, they're carts. There's a green square with a little circle, that's the human pushing a cart. There's a red oval, that's the robot, and then there's a red oval with the green square on top of it. That's the robot carrying a cart. So you're assuming the robots in this example are doing the long travel from zone to zone, from zone off to packing or zone off to sorter and back to shuffle the carts around. But the picker then is directed to specific carts, and if it will start the movement on it, and you'll see the pickers moving around, pushing the carts. You'll see the robots transferring carts from zone to zone or zone off to packing. You may have noticed pickers were walking from zone 2 to zone 3 or zone 3 up to zone 2. So it opens up possibilities for the dynamic work optimization to actually make significant improvements in the batching that they do because I've opened up the travel paths to be more efficient. I'm going to, that's the end of that scenario. Again, like I said, in the future you may see a webinar from us to dive more detail on how that will work and provide you more efficiency. I'm going to turn it back over to Krishna for a summary.
Great, thanks, Dave. So a couple of things. So what we did not mention earlier is Lucas Systems is not in the business of manufacturing these robots. As you saw from the slides, we're working with other robotic systems, not all of them that we showed, but we're working with robots that are already being manufactured. Our focus is to build math-based optimization software to make the work and the execution of that work more efficient. And that's the focus that we have, and that's what Dave just walked us through. So the objective of what we're doing with our software is to take the pool of work, optimize it so we can maximize the labor and the productivity of the humans working in these operations while optimizing the usage of robots, right? So that's the goal, and that's the objective of our software. We work with any kind of WMS and other automation systems that our software sits in between these systems, optimizes the work, and hands it over to the right technologies, including our voice-based work execution system that actually directs the human, the picker, or the person who's doing the job. And that's how the entire system comes together. Again, the objective here is to optimize that work, and I hope we have conveyed that message clearly to you this afternoon. Thanks for taking the time. I'll turn this over to John now.
Great. Thank you very much, Dave. Like I said, we're going to be doing our Q&A session now. Feel free to type in your questions on the screen. We've had a few come in already. We are also, again, if we don't get to your question, we will answer them after the webinar is over. So the first question is actually very voice specific. And this is the voice in the headset a human or a computer-generated voice? Krishna?
Yeah, so the voice application or the instructions that guide the person, the human in this use case, is through our Lucas's voice solution called Jennifer. And the voice is actually a human-recorded voice, and the workflow for that voice application is designed through the Lucas software. So it's It's a Jennifer Hour voice that actually talks to a person, which is a human voice.
Right, human voice, right? Now this next question, doesn't the tablet on the robot tell the worker the next pick location? I think this is referring to the first scenario, Dave, that you were talking about. So there is a tablet on the robot. Doesn't that give the user the instructions?
Yes, it does. It will tell them which pick to make right now, and often they have the next pick on the display. But the human has to make decisions as they do that as to whether that next pick is the right one, or if they have another robot nearby, is this other robot the right one? And often we're like, if you saw in that scenario, the robot leaves the aisle that they're in, their decision point is what they see in front of them. So they can't make as intelligent a decision based on what the next 2, 3, 4 picks are as to what's the best path for them to go. So without that total picture of what all of the robots are doing in coordination around them, they're not going to make the optimum decisions all the time.
Okay. Great, thank you. The next has to do with pre-planning work. So is the software pre-planning waves of work, or is this creating work in a waveless fashion?
The short answer to that is in a waveless fashion, but it's, as you may have caught in the name of the module we use, is our dynamic work optimization. It is dynamic. As the work is coming in, typical today's world with e-com, orders are coming in all day long and feeding into the system to be picked today. So as that work's coming in, it is adding that work to the algorithms and processing it dynamically as the worker goes along and as the robots are traveling around.
Great, thank you. Here's a question. Okay, let me paraphrase this a little bit. Would it be more productive to increase pick density by creating bigger batches for conventional cart picking rather than using multiple robots with smaller batches?
Oh, absolutely. Creating a bigger batch is more productive, but when I create bigger batches, if I have long travel and distances to travel to do that, I may want to have that assisted by a robot making that long travel for me. But that's, again, what our dynamic work optimization does, is create these batches so that they are efficiently picked based on the equipment, cart sizes, and cubing of the cartons and totes that need to be transferred on or pushed along on carts.
Okay, this next question is kind of just a clarification. So have you integrated robotic arms at all? And if so, what application and benefits are there? I think.
Yeah, so robotic arms, no, we have not interfaced with. Again, we can, but we have not delivered or piloted a solution with arms, primarily because the arm systems that we looked at were not, they did not apply to the industries that we tried to solve the problems for. Not to say that those systems are not reliable or prevalent now, but we have not had the experience of having one in pilot/production that we can talk about.
Okay. Let's see. And which actual system is creating the work assignments in the scenarios where the workers and the robots are collaborating? Is it the robot system creating the work, or is it the Lucas system?
So every robot vendor provides their own software that does the optimization of work and dole out the work to robots. However, what we've explained today is the Lucas software taking work from a warehouse management system or an ERP, doing the planning and of the work execution so it can coordinate the work, the actual order fulfillment process between the robots and the humans. So we sit between WMS and the robots and the humans and provide the work that the robots need to execute. So basically we pass that control to the robot control system or robotic management software, which then gives it to the right robots and ensures that they give it to the right individual robots that need to execute the work. So all the math, the optimization of the work is done in the Lucas software.
Okay, this goes to a question about WMS integration. So how would this robot-human system interface with an existing WMS?
Like I said, the Lucas system software sits between the WMS and the robots in this case. So much like how we've interfaced, Lucas has interfaced with any warehouse management system, may it be a commercial packaged warehouse management system or a homegrown warehouse management system or an ERP. We've built those interfacing capabilities into the Lucas software already, and we've done that for the last 20 years. We use that capability to exchange data with the warehouse management systems, optimize the work, dole out or hand out the work that the robots need to handle to the robotic control systems, while allowing the pickers to pick using the Lucas Jennifer voice execution system.
Okay, and there's one more. So does Lucas recommend the actual AGVs that a customer could use? And I think we want maybe clear up AGVs versus robots.
There are uses for AGVs. How I clarify the difference between an AGV and a robot. AGVs are traveling a set path. There's paths through the warehouse that they will stay on and travel, where the robots are more free movement, where they can move around the warehouse and provide you more value in that ability to be free moving. Now, that doesn't say there aren't applications that the AGV is a more appropriate solution to the problem or use case. Thank you, Krishna. To the use case, and so there are applications where AGVs make a lot of sense. Equally, applications where the robots make a lot of sense.
Okay, great. All right. Well, that takes us up to the bottom of the hour. It's about 1:30. Thank you, everyone, for your questions. Again, if any other questions come up, feel free to email me at that email on your screen now, or call Lucas Systems. Likewise, there's more information on the Lucas website at lucasware.com. Thank you again for joining us, and we look forward to seeing you on a future webcast. Thanks very much.